Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the Gibbs phase rule, the Clapeyron equation, and the saturated vapor pressure equation. Firstly, let's talk about the Gibbs phase law. Although thermodynamics laws apply to all material phases, in practice, we mostly focus on compressible materials like gases and liquids when discussing thermodynamics-related topics. In general, properties are divided into two groups: intensive thermodynamic properties and extensive properties. The intensive properties like temperature, pressure, and specific volume are usually considered as independent variables as thermodynamic coordinates. For pure substances, we need only two of these independent variables, and the third one can be determined as a dependent variable or as a function of the selected independent variables. The F number of required independent variables or degrees of freedom can be determined using the Gibbs phase rule. For C number of components with P number of phases, the Gibbs phase rule gives. For example, for a pure substance like water in a liquid phase, we have C equals 1 and P equals 1, which gives the number of independent variables needed as F equals 2, using equation 563. Therefore, two thermodynamic properties like pressure and temperature are sufficient to determine water-liquid properties at any state point. Note that the function of independent variables is the equation of state. For example, an ideal gas. If we have water in a state with two phases in equilibrium, like a liquid-vapor mixture, then we get C equals 1 and P equals 2, which gives 1 degree of freedom, using equation 563. Therefore, one property is sufficient, like pressure or temperature, to determine the water-liquid-vapor mixture. Another important result of Gibbs rule is the maximum possible phases with the constraint of F. This requirement gives P max. Therefore, for a single component substance, we get P max. This usually defines the three-phase equilibrium and triple point for single species material. Secondly, let's talk about the Clapeyron equation first. The Maxwell relations have far-reaching implications in thermodynamics and are often used to derive useful thermodynamic relations. The Clapeyron equation is one such relation, and it enables us to determine the enthalpy change associated with the phase change from a knowledge of P, V, and T data alone. According to the third Maxwell relation, look at the PT diagram, the slope of the saturation curve on a PT diagram is constant at a constant T or P. During a phase change process, the pressure is the saturation pressure, which depends on the temperature only and is independent of the specific volume. That is, therefore, the partial derivative can be expressed as a total derivative, which is the slope of the saturation curve on a PT diagram at a specified saturation state. This slope is independent of the specific volume, and thus it can be treated as a constant during the integration of the third Maxwell relation between two saturation states at the same temperature. For an isothermal liquid-vapor phase change process, for example, the integration yields where the subscripts A and B represent the two phases in the phase transition process, respectively. Equation 564 is the Clapeyron equation after the French engineer and physicist E. Clapeyron, also known as the Clapeyron-Clausius equation. During this phase change process, the pressure also remains constant. Therefore, we have, based on equation 565, we have, this is an important thermodynamic relation since it enables us to determine the enthalpy of vaporization at a given temperature by simply measuring the slope of the saturation curve on a PT diagram and the specific volume of saturated liquid and saturated vapor at the given temperature. The Clapeyron equation is applicable to any phase change process that occurs at constant temperature and pressure. Now, let's talk about the saturated vapor pressure equation. The Clapeyron equation can be simplified for liquid vapor and solid vapor phase changes by utilizing some approximations. At low pressures, we have specific volume of vapor much larger than that of liquid, and thus the volume difference of vapor and liquid is very close to the volume of vapor. By treating the vapor as an ideal gas, we have this relation. Substituting these approximations into equation 565, we have equation 566. For small temperature intervals, the enthalpy of vaporization can be treated as a constant at some average value. Then, integrating this equation between two saturation states yields. This equation is called the Clapeyron-Clausius equation, and it can be used to determine the variation of saturation pressure with temperature. It can also be used in the solid vapor region, by replacing the enthalpy of vaporization with the enthalpy of sublimation of the substance. Equation 566 can also be expressed as: if the temperature change range is not large, the enthalpy of vaporization can be regarded as a constant. Then, this formula shows that at lower temperatures, ln P saturation and 1/T saturation have a linear relationship. Although the above formula is not precise, it provides an approximate method for calculating P saturation under the same T saturation. Or we have more accurate relations. Okay, that's all for this task. Thank you very much, and see you next time.